let's look at the idea. If the function is not linear, we learned in the first lesson of this module how do we linearize the nonlinear function. Means regardless what kind of curve you have, the linearization is nothing more than you get the tangent line in the 1D, and then you consider this red tangent line to approximate the blue curve, which is not linear. If you go to 2D, you just change this red line into a tangent plane and the blue curve into a curved surface, so on and so forth. So when we deal with the extended gamma filter, all we need is add one more step. Just use the Taylor's series to make a linear approximation. That's the whole idea. We call this technique as linearization. Well, when you do this approximation, all we need is our time step is this dt very small. If it's sufficiently small, the difference between the red line and the blue curve is negligible. That's the whole idea. So to choose the small time steps, the linear approximation and can make the linear gamma filter to work for the nonlinear error model. So this is the idea. Now the outline today is, first we look at the nonlinear measurement and the control system. And then we review how to use the Taylor series. You remember the gradient, Jacobian matrix, to linearize the measurement and the control function. And then we give you the algorithm of the extended gamma filter, in short, EKF. And finally, we're going to give you an example in MATLAB. Now, let's look at the previous linear filter. In the linear gamma filter, it's basically governed by this. We call it a prediction model. And this one is the measurement. And the most important parameter are this matrix and this matrix and this. All these three matrices are constant matrices in the previous lesson for the linear model. Well, I first have to explain to you a little more about what means linear, what means nonlinear relationship. When we learned the linear regression, you remember we assume the chicken eat more when it's heavier. So we assume the food the chicken is consumed has a linear relationship with the weight of the chicken. And we got this regression line like this. That is, you can say, hey, yeah, of course, the more heavier, the more food this chicken eat. But give you another relationship. Let's look at the percentage of our income spent on the food for the human being. Is that percent of the income a linear relationship with the income? The answer, of course, no. Because the rich people, the two super rich like millionaires, they don't spend 1% for their food. But the poor maybe need to spend 50% of their money for the food. And of course, you can imagine the relationship if this is 100% and this is the income in this way. The more income, the less percentage they're going to use for their food. But it's not going to be a straight line. So what it look like? It will probably look like this. The poor people have a big percentage, almost all for their food. And the rich people almost have nothing. Like Bill Gates spent almost 0% money for his food. So it's not linear. So the relationship is determined by the phenomenon, the application itself. The mathematics model try to be most fit into the application, means accommodate this relationship. So you cannot change the model itself, but we can use the approximation to solve the problem. Again, I want to remind you, do you still remember when we talk about the transformation? There's a linear transformation and the nonlinear transformation. When we talk about the linear transformation, the relationship is always the y equals a times x. And this a is a constant matrix. But for the nonlinear, you cannot do that. You don't have such a matrix. You might have to write this y if f of x. But at that time, when we talk about the nonlinear transformation, we did not go further. We just tell you, hey, you cannot just write it into a matrix. You have to write it into a general function. And I give you an example like this, I remember. Y equal x1 times x2 plus x2 square, y2 equal x1 square minus x3 square, y3 equal x1 square. You see, with all those square, you know it's not linear. But you cannot write into a matrix like this. So the bottom line is these two will be changed when we talk about nonlinear model. So let's start from one example. It's clearly not linear. If I let this x2 be a constant, you see the k is the time. And x2 at the time k equal the same as x2 at k minus 1. Means doesn't matter what time, the frequency, he write in this way, and the actual should be that way. The frequency is a constant in this example. But the function itself, let me call this frequency x2 be the omega, like what you used in calculus. And then my x1 is a function of t equals the sine omega times t minus 1. This relationship, you know, is a sine wave like this, if it's in a perfect situation. Of course, you agree with me. This is not a straight line. It's not going to be linear. It's very high nonlinear. So if this relationship f is not linear, actually the f is, let me write into what you easy to read, is x omega equals sine omega t and the omega itself. And this you cannot write into a matrix times x and omega. So it's not linear. All right, what is it? It's a sinusoid wave. You're going to do that probably in the summer research with the nonlinear wave tank. Why nonlinear wave? I know all waves are not linear, but I don't know why it's nonlinear. I asked Dr. Ludu. The AUV have to constantly adjust its orientation because you have to avoid some obstacles on the trajectory. And then when you do the maneuver and to change the orientation, each time you're going to multiply a different rotation matrix. But as I pointed out a moment ago, what is the rotation matrix? R equals cosine theta t, sine theta t, and the negative sine theta t, and the cosine theta t. And of course, those trigonometric functions, as we pointed out, it's not going to be linear. But this time is the control variable u, not linear. The previous example is the transition matrix relationship f, not linear. The third example, when you look about the GPS signal, you'll find that the distance formula, and we pointed out before, that's not linear, of course. So you got a bunch of examples, you have to change into the linear function. So how do we write the nonlinear Kama filter? The step 1, see what I changed? The previous one is xk equal a xk minus 1 plus b uk minus 1 plus wk. But this time, I put these two together into a function f. Well, this f, of course, it's a multi-variable, multi-components function. Okay, let me point it out again. It's a multi-variant, multiple variables, and also multiple components. That means it's a vector. That is a vector function. And then we add this noise. The wk is the variance. Some other context maybe even write this together with the 3 variables, but that's fine. At this stage, we don't know what is it, but we just know it's not linear. And similarly, for the measurement, this time in the linear model is this, right? And you have this matrix H. But if it's not linear, I need again use a general function. Use a general function. So this is the difference. Other than this, of course, you all have this noise. The covariance is basically I follow the multivariant normal distribution, and so it's here. So this is our math model.